Okay, we've seen that the electric field of our charge rod behaves just like a point source when you're a long way away, behaves like an infinite cylinder when you're close. But what about the more realistic case where you're neither close nor particularly far away, but just sort of middle distance? What's going on here? Well, to do this, what we're going to do is make the approximation that our cylinder is actually a whole bunch of point charges all the way along. And if you want to work out the electric field at some location, like say here, what we will do is we will work out the electric field due to the first point charge, electric field due to the second point charge, electric field due to the third point charge, and so on, and we get a whole bunch of vectors. And we'll add up all the vectors to work out the net electric field. That's all there is to it, just lots of adding up. Now we can do this adding up numerically on a computer. Computers are good at adding up large numbers of small things. Or we can do it via calculus, which is, when it works, even better at adding up infinitely small things in vast numbers. But to do either, we're going to have to work out the step equation. In this case, our steps are going to be little slices across here. And we need to work out the contribution of each slice to the electric field at some point over here. And then we're going to need to sum all the way up and down the rod to work out the total electric field at some point. So let's set up some coordinates. Let's call that distance x, and this distance up here y. And the charge of that little slice over there we'll call delta q. And the vector from that location up there to where we're trying to measure the electric field is r, as usual. Okay. Now we're assuming that the cylinder is very, very thin, so we can take this tiny dq thick cylinder and treat it as a point, which will be fine as long as your distance x or r here is much bigger than the thickness of the rod, which is probably going to be the case. Okay, so let's try and work out what the electric field is going to be here. It's going to be a vector, so we're going to have some electric field, some little bit of electric field, delta E here. Now what is r? The displacement vector is the end position minus the starting position, so that's going to be x minus 0, 0 minus y, so minus y, and 0 minus 0, z. So that's our r. Pythagoras' theorem tells us the length, the modulus of r, is going to be root x squared plus y squared. The fact that it's minus doesn't matter when you square it, because minus times minus is plus. Therefore, we know that from Coulomb's law, the electric field is equal to 1 over 4 pi epsilon naught, 1 over mod r squared r hat, where r is a unit vector in this place, just to give it direction. We can also remember that r hat is just equal to r divided by mod r. That's the definition of the unit vectors. So that comes out as 1 over 4 pi epsilon naught 1 over mod r cubed times r, which is a slightly simpler way of writing the same thing. Now we know what r is, we know what mod r is, so that tells us that if we break it into components, delta E is equal to 1 over 4 pi epsilon naught, this is 1 over x squared plus y squared to the 3 halves, because the square root is to the half, so the half cubed is 3 over 2. And then we've got our vector x minus y 0. Oh, we also need to put the charge in here, delta Q. One final step we need to bear in mind, as we saw last time, the thickness here is delta Y. The charge, delta Q, is just going to be equal to delta Y over the total length L times the total charge Q. Just saying the fraction of the charge is uniformly spread, so the fraction of charge in this little slice is just equal to the fraction of the length in that little slice. So put that all in, we end up with the little bit of electric field caused by that bit is and that is our step equation. What we'll need to do is, whether numerically or by calculus, go up and down the rod and add up all these little contributions from all the dy's, and that will give us the x, y and z component of the electric field here when we add them all up.